Hello dear students, we'll start our lesson. This is lecture 2 in Higher Mathematics 2, which we call the theme Limits and Continuity in Higher Dimensions. Okay, let's start our lesson. We start with definition. We say that a function f of xy approaches the limit L as x and y approach the point xy approach the point x0, y0, and we write this expression, which is limit when xy tends to x0, y0, and the limit of this function f of xy tends to L. We've learned a similar notation with the function single variable. For example, we had this kind of notation, limit x tends to x0, f of x is L. We already know this one, but now we are extending this expression for the function of two variables, x and y. And this expression, just now we read that for every number epsilon positive, there exists a corresponding number delta positive, such that for all xy in the domain of f. So these two statements or conditions are whole met, which is if we subtract the L, which is the limit from our function, we have to get some number positive epsilon, which is epsilon is extremely small number. This square root also should be between 0 and delta. And here's the explanation of this one in the graph. You may see this is the function's domain, which is written with D. This is the domain. And now we have a function with double variables, which is two variable function xy. So the domain is this kind of area. It's not just a line, it's area. We have x's and y's, and this is our point xy. It's tending to the point x0, y0, to this point. It tends to this point. And what is delta? Delta is this radius, the radius of this one. These 2 points should be extremely close to each other, and delta is this number. It also should be smaller, but we come from the epsilon. Epsilon is for the function's value. As we may see from the previous slide, the function's value subtracted from the limit, we have to get extremely small positive number, which is epsilon. So even if function has two variables, like x and y, it will have one single value at every point. So the function's value, which is we have domain and range. The range is from this z-axis, and we have this limiting point L, and this is the function's value at point x, y. And epsilon is this one, this small part. We call this yellow part epsilon. In the limit definition, delta is the radius of a disk centered at x0, y0. For all points xy within this disk, the function values f of xy lie inside the corresponding interval, which is L minus epsilon and L plus epsilon. As for functions of single variable, it can be shown that limit of x is x0 and limit of y is y0, while limit of x is x0. In this case, it says to me or to you, plug in instead of x, x0, and plug in instead of y, y0. So do I have x here? Yes, it's here. So just write instead of that x0. Do I have y here in the function? No y. No y. So we don't have to write it. And in this case also, write y0 instead of y, copy the x0 instead of x. So do I have x here? No x. But y? Yes, of course, we have y. So instead of y, I will write y0. In the third case, plug in x0 instead of x, plug in y0 instead of y. So what will I get here? So do I have x? No. Do I have y? In this example, no, I don't have. So the answer is same. Answer is k, because k is any constant number. It's a number. K is constant. Limit of constant. Here are the theorem 1, which tells us properties of limits of functions of two variables. These rules are same with the function of single variable limit. We've learned in the previous course, which is Higher Mathematics 1, there was 7 rules. All of them applicable here. Now we'll see how it works, why it works. So the following rules hold if L, M, and K are real numbers, and limit when the point xy tends to x0, y0 of function f of xy is L, and the limit of the function g of xy when xy point tends to x0, y0 is M. In that case, we may check some rules now. So the first rule says limit of f of xy plus limit of g of xy when xy tends to the point xy tends to point x0, y0. Point x0, y0. We don't know their sum, but we know their limits calculated separately. So I know the limit of f of xy is L from here. From there it was L, and I know the limit of g of xy is M. I know from here that one. So we just wrote L plus M. Or in the next one it says when the difference of these two functions, f of xy minus g of xy, and I need to find the point xy tending to x0, y0. So the limit will be the difference of limits. So f of xy's limit was L, and g of xy's limit is M. So the answer is L minus M. Constant multiple rule. Constant multiple rule. Now we have just one function, which is f of xy, but if you look carefully here, you may see that the f of xy is multiplied with k. So k is a constant number. Just wrote k first, and then write the limit of f of xy, which is L. And using that rule, we can create a new rule, which is called product rule. The first rule, product rule. In this case, limit of f of xy multiplied by g of xy. So limit of f of xy is L, and g of xy is M. So it can be calculated directly like this. For example, if I have a limit xy tends to 1 and 2, and my function is x squared y equals to, if I plug in 1 here instead of x squared, I will get here 1 and 2. So the answer is 2 now, and one which is limit xy tends to 1 and 2. Let me get another function which is just x, y. Okay, plug in 1, 2. It's also number 2. Let me say here like 2, and it should be different from the previous one, so it is 4. Now we can calculate some rules. The first rule is sum rule. The limit when xy tends to 1 and 2, and the functions x squared y plus xy squared. So x squared y is f of xy, x squared xy squared is g of xy. According to the sum rule, the first rule, I have to write here L plus M, which is L is, in my case, it's 2 plus 4, and it will be 6. Now I have calculated. It can be done for all other rules. For the difference rule, it will have negative sign here, and with a negative sign we'll get negative 2. And for constant multiple, if I write instead of k, for example, 7 times 2 will be 14, or if we take the product of these two functions, we'll get the number 8. There are some other rules which call quotient, power, and root rule. Quotient rule. In the quotient rule, f of xy over g of xy. In this case, g of xy's limit, which is the number m, cannot be 0. M is not 0 because we cannot divide by 0. Can't divide by 0. So according to our previous function, I can write here limit xy tends to 1 and 2. My functions is x squared y over xy squared. There are two ways to calculate this one. Two ways. First one is simplifying this. Second one is using quotient rule. Just use quotient rule here, because we already know the limit of x squared y is 2, xy squared was 4, so this is 1 over 2. The next one says power rule, power. Let me take another color here. Okay, in the power rule, I'll write here limit xy tends to 1 and 2, and here I will have x squared y to the 8 maybe. Okay, 8 equals to, the first way is to calculate this power, second way is to calculate limit and then power. So I know the limit of this one was 2 and the power is 8. 8's power of 2 is, I think, 256. I think 256. Okay, now in another example, in another rule, root rule says the inverse part of this one, because nth root of f of xy. So the limit xy tends to 1 and 2, our function is cube root of f of xy equals to, so I know the limit of f of xy was 2, so cube root of number 2. In this case, n is a positive integer, not a positive integer, and if n is even, we assume that L. In this example, we can combine the three simple results following the limit definition with the results in theorem 1. To calculate the limits, we simply substitute the x and y values of the point being approached into the functional expression to find the limiting value. So in this case, it says first we have to calculate the limit xy tends to 0 and 1, and the function is x minus xy plus 3 over x squared y plus 5xy minus y cubed. So in the first case, we have to calculate this one. This says to me write 0 instead of x and write 1 instead of y. So all zeros instead of x's. 0 minus 0 times 1 plus 3, and 0 squared times 1 plus 5 times 0 times 1 minus. Second one is also says write 3 instead of x, and also write negative 4 instead of y. So 3 squared plus negative 4 squared. Calculate this expression and get the number 5. Example 2 says find the limit when xy tends to 0, the point 0, this expression. Okay, we may think that plug in 0 instead of x, plug in 0 instead of y. Okay, 0 squared minus 0 times 0 over square root of 0 minus square root of 0. So this is 0 over 0, undefined. This is undefined. We cannot divide by 0. Can't divide by 0. So since the denominator approaches 0 as xy, the point tends to 0, we cannot use quotient rule. Can't use quotient rule from theorem 1. Quotient rule. Can't use quotient rule from theorem 1 right now. And if we multiply numerator and denominator by square root of x plus square root of y, however, we produce an equivalent fraction whose limit we can find. Okay, let us try. So multiply this expression's positive part to both of them. Multiply from 2, 1. Okay, now go further, and here you may see if we multiply this together, and we'll get x minus y here over that expression. Let's take x outside of parentheses, x minus y, square root of x plus square root of y. We'll get this expression as you may see here. So now there are x minus y's are gone here, and just left x plus y and the square root. So now I can plug in this 0 instead of x and that 0 instead of y. The answer is 0. We can cancel the factor x minus y because the patch y equals to x is not in the domain of the function, domain of the given function. With functions of a single variable, continuity is defined in terms of limits. Definition says a function f of xy is continuous at the point x0, y0 if f is defined at x0, y0. The first one, f should be defined. Second rule says limit of when xy tends to the point xy tends to x0, y0, the limit of the function exists. In the third case, limit of function and the function's value should be equal to each other. For example, let me create a function here, f of xy equals to x squared y cubed. Okay, this is the ordinary function. Now I want to check the function's continuity at a point. Let me say xy tends to 1 and 1. So let's check. The first one, f is defined. Let's plug in these numbers here. Plug in numbers. If I plug in these numbers, I will get f of 1 and 1, which is equals to 1 squared times 1 cubed. Gives me the number 1. Okay, the second one says limit xy tends to 1 and 1, and the function is which is f1 and 1. Okay, I'll copy this again. Limit xy tends to 1 and 1, and the function is 1 x squared times y cubed. Just plug in these numbers here, 1 squared, 1 cubed, which is 1. And the third one says these two should be equal to each other. Equals to 1 and 1, because this is also 1 and that one is also 1. And here the interesting one, it says a function is continuous if it is continuous at every point of its domain. Two-patch test for function. We also have two-patch test for non-existence of a limit. If a function f of xy has different limits along two different paths in the domain of f, as the point x does not exist. Where did this come from? In the higher mathematics 1, we also learned left-hand limit, right-hand limit. If you remember, we wrote like this: limit x tends to 2 from left side, or limit x tends to 2 from right side. If we have this number line and the 0 here and number 2 here, we approach from this part and we approach from that part. If these two limits are not equal to each other, limit does not exist. And it's the same with this one, which is the function with double variables. Having the same limit along all straight lines approaching x0, y0, the point x0, y0, does not imply a limit exists at this point. Continuity of composites. We also learned the composite functions, which is the complicated functions. There are some functions inside of another function. We call that composite function. If f is continuous at point x0, y0, and g is a single variable function continuous at f of x0, y0, then the composite function h equals to g composite by f. We read this defined by h of xy equals to g of f of xy is continuous at this point. If you remember, we read this one, g composed with f or by f. We read like that. For example, the composite functions here. Here we have two functions, the f and g. And g of x is e to the x, f of xy is x minus y. So this is the composite function, and this one is also g of x here. G of x is cosine of x, and f of x is xy over x squared plus 1. And in this case also, ln x, g of x is ln x, f of x is 1 plus x squared y squared, not xy here also, and here also xy, not just x, are continuous at every point xy. This e is extra, don't need that. Functions of more than two variables. The definitions of limit and continuity for functions of two variables and the conclusions about limits and continuity for sums, products, quotients, powers, and composites all extend to functions, sums, products, quotients, powers, and composites all extend to functions of three or more variables. Functions like ln x plus y plus z and this kind of functions are continuous throughout their domains and limits like this, where P denotes the point x, y, z, may be found by direct substitution.